In this video, I'm going to look at how chemists deal with the minute size of atoms when they measure amounts of substance. So hopefully by the end, you'll understand the concept of the mole. We'll start off by looking at the mass of a typical atom, and hopefully you'll appreciate that these are so tiny, these numbers, that we have to scale up to something more manageable. The example I'm going to use is carbon-12. So the carbon-12 atom could be represented like this. So we've got the symbol C and we've got the 6, which stands for the atomic number. So that's the number of protons in the nucleus of the carbon atom. And we've got the number 12 there, and that's the mass number for this carbon-12 isotope. Because the atomic number of carbon is 6, that tells us we have 6 protons. Remember, they're positively charged, and to keep the atom neutral, which it must be, it must therefore have 6 electrons as well. The mass of the atom, the 12, well, the particles that make up the mass of atoms are the protons and the neutrons, and so if we've got 6 protons, there must also be 6 neutrons, and remember, the quick way to work that out is to subtract the small number from the large number. And you can see there I've starred the protons and neutrons because they are the particles with some mass worth speaking about. Obviously electrons do have a mass, but it's so tiny in comparison to the protons and neutrons, we're going to ignore their mass. The mass of a proton is the same as the mass of a neutron, and there's the mass written down for you in kilos. So the mass of a carbon-12 atom is going to be this number here multiplied by 12, because we've got 6 protons and 6 neutrons. So there you go, there's the mass of a carbon-12 atom, 1.992646538 times 10 to the minus 23 grams. So imagine doing a calculation where you had to use numbers like that. It would be a nightmare. So what the scientists decided to do was they would scale this number up massively to end up with a number that was a lot more manageable to work with. And the number that they used to scale up, I'm sure you've come across it, is this number here, 6.02 times 10 to the 23. I'll tell you what that number's called in a moment, but let's just see what effect that has on this number here. So that's the mass of one carbon-12 atom, and we're going to multiply this by this number here. So you can see that multiplying this number by the mass of the atom, we get this 11.99573216 grams. So that rounds nicely to 12.0 grams. So hopefully you're going to be familiar with that number for carbon, because that's actually the mass number for carbon that we see on the periodic table. So what is the mass number? It's actually the mass of this many atoms. So this is a pretty special number, and it was named after a pretty special scientist called Avogadro. So this is called Avogadro's number. Sometimes it's given the abbreviation capital N and then a subscript capital A. Avogadro's number. Not avocado's number that I sometimes see when I'm marking students' work, although it does make me laugh. So these manageable numbers that we've created, these are the numbers that we see on the periodic table. And these numbers represent the mass of this many atoms. So just like you can have a decade representing 10 years, a century representing 100 years, a dozen representing 12 of something, you can have a mole, and that just represents Avogadro's number of things. In this case, we're talking about atoms, and you'll see later on in the video you can actually have a mole of anything, because a mole is simply just this number. So there's the definition of the mole for you. So it's the amount of any substance that contains the same number of particles as there are carbon atoms in 12 grams of carbon-12. So remember, we've just worked out that in 12 grams of carbon-12 there are 6.02 times 10 to the power 23 number of atoms. There's a handy formula triangle that links all of these terms together that we've just been talking about. So if we know the mass in grams of a substance and we know its MR, its relative mass, we can work out how many moles we've got. So I'll just feed the numbers in for the carbon example. So we've just said that if we've got 12 grams of carbon-12, so the MR is 12, you can see obviously we're going to get 1 there, and that refers to the number of moles. So that's 1 mole from the 12 over the 12. And of course, once we know how many moles we've got, we can find out how many particles we've got simply by multiplying by Avogadro's number. So if we've got 1 mole of carbon-12, which we've just calculated, how many particles will be present, and by particles in this case I mean atoms, we've obviously got 6.02 times 10 to the 23. There's 2 handy formulae for you. So there's the mass moles MR triangle, and the number of particles equals the moles times Avogadro's number. If you just have a think about the information on the board now, what have the following all got in common? So we've got 24.3 grams of magnesium, 58.7 grams of nickel, and 107.9 grams of silver. I'll give you a clue. You need to be looking at the periodic table. Hopefully you've all realised that we've got 1 mole of each of these substances. So because these are all 1 mole of the substances, we can also say how many particles are present. So, and by particles, we're talking about atoms here, so the particles are the atoms involved. So we would have Avogadro's number of magnesium atoms in there. In the 58.7 grams of nickel, we'd have Avogadro's number of nickel atoms. And in the 107.9 grams of silver, we'd have Avogadro's number of silver atoms. Now, you don't just have moles of atoms, you can also have, well, you can have moles of anything really, but these are molecules now. These are water molecules. You can have a mole of water molecules. So basically, we've got 1, 2, 3, 4, 5 water molecules on the board now. If we wanted a mole of water molecules, we would need Avogadro's number of water molecules. In other words, the same number of atoms as are in 12 grams of carbon-12. So we'd need Avogadro's number of these to have a mole of water molecules. So how many grams of water would we need to have a mole of water? So we want 1 mole of water, so the N is 1. That's what we want to work out. How many grams do we need? The MR of water, well, H2O, so that's 2 plus 16, that's 18. So if we multiply 1 by 18, we get the mass, so we need 18 grams of water, and that's a mole of water. And inside that beaker of water, there would be this many of these molecules. Now sometimes in exams they sort of crank up the difficulty levels by then going on and asking how many atoms are in a mole of water. So if you just have a look at the information that's on the board now and see if you can work out how you would do that. So obviously if we've got Avogadro's number of these, there are 3 atoms in each of those, so we just simply multiply Avogadro's number by 3, and that gives us that number of atoms. It's always important that you know what you're talking about. Are you talking about molecules? So that's the whole group of the atoms. Or are we talking about atoms, which is obviously the individual atom that make up the molecule itself? We'll finish with this question. So I've just found the emissions data for my car. So it produces 144 grams of carbon dioxide for every kilometre that I drive. So using what you've learned so far from the video, can you work out the moles of carbon dioxide per kilometre, the number of molecules of carbon dioxide made per kilometre, and how many atoms per kilometre that would equate to? So pause the video, have a go at the calculations, and then play and see if you get them right. So the first one, the moles of carbon dioxide. Well, we know that the car makes 144 grams every kilometre, so that's the mass. The MR of CO2 is 12 plus 16 plus 16 is 44. So it's 144 divided by 44, and that comes out at 3.2727 and so on. So we'll say 3.27. We'll just do three significant figures. 3.27 moles. How many molecules, how many of these things will we have coming out every kilometre? Well, we've made 3.27 moles. 1 mole equates to Avogadro's number of molecules. So we're going to have the moles multiplied by Avogadro's number, and that comes out at 1.97 times 10 to the 24. 1.97 times 10 to the 24. How many atoms are we talking about? Well, in one molecule, there are 1, 2, 3 atoms. So if that's how many molecules we've made, we multiply that by 3 to get the number of atoms. And that comes out at 5.91 times 10 to the 24. Apologies in advance for my poor artistic drawing skills, but we've got a map of Great Britain there, an outline of Great Britain. I've put a couple of important places on just to give you some reference points, and the reason I'm going to talk about this is to try and get our head around just how big this number is, Avogadro's number. So if you imagine you had a mole of sand, so I'm sure you can all visualize sand. If you covered the entire Great Britain with sand, they think that the pile of sand would be 1,500 kilometers high. Now that little fact links in nicely with the derivation of the word mole, or the origin of the word mole. It actually comes from a Latin word which means massive heap. So obviously that would be a pretty big heap of sand, 1,500 kilometers high, covering the entire British Isles. And I'll finish with this. You may not be aware that Mole Day is celebrated on October the 23rd each year, and it must start at 6:02 AM and it must finish at 6:02 PM precisely. And we always have a right laugh when we celebrate it. We do loads of mole calculations and stuff like that. It's absolutely brilliant. So like I say, we celebrate it every year. Here's an example of the poster that we used for the 2012 Mole Day, and make sure you celebrate it because it's a very, very important day.